All right, friends, this is 4.3. This is just from last day, and so it's just here just as a kind of a reminder. This was the assignment. If you have questions, post them, email, what have you. Oh, great, I've already screwed up the order here. All right, there we go. This is today. I'll get that in better focus. This doesn't have everything, so I'm going to let you write that title down. Static and kinetic friction problems. You're going to pause that if it's too quick, and then that's the whole page. Let you pause that. Okay, good note taking. Static friction. This is touch review, but building on it. Static friction must be overcome for motion to occur. If more than one object is attached or connected, the combined maximum force of static friction must be overcome. Static friction is also necessary for movement. So imagine walking on ice without any friction. There's good and bad results, I suppose, of friction. Kinetic friction. Kinetic friction acts on a moving object in the opposite direction of motion. So it will slow you down. Sometimes that's a good thing too. Consider figure 8, page 175. It just shows that kinetic friction can work with you or against you. So if it's working against you, like if you're trying to push something, push a big heavy cardboard box across the floor, kinetic friction is working against you. If you have something sliding towards you and you want to stop it, kinetic friction will be working with you. Net force is applied force plus kinetic friction. That plus may be a negative if it's working against you. Okay, remember, like, these forces have vectors. So one might be to the left and this one might be to the right. Just depends. There is lots of practice questions. I'm already going to break a promise, I think. I told you guys I would do every single one. Goodness gracious, there's a ton to do. So this video will be an hour long, I think, if I do them all. I'm already curious about how long it's going to be. But generally speaking, I'm going to do the practice on page 174, practice on page 175, and the practice on page 177. So it's going to be a lot. Get comfortable, but I guess that's also why you have a pause button. This is your assignment, 178, 1 to 10. Oh, look, excited for what's coming next. I'm going to make a mark so I don't lose my spot. I don't know what that is. Maybe today I'll clean my office. Maybe not. All right. So let's try and get a good picture here. Anybody watch Blue's Clues? All right, where are we starting? Page 174. Number 1. Here we go. It's going to be fun. It's going to be long. 2 trunks sit side by side on the floor. The larger trunk, 52 kilograms, is to the left of the smaller trunk, 34 kilograms. Okay, so M1 equals 52. I don't even know where this is going yet. M2 equals 34. I'm just writing stuff down, just getting it out. A person pushes on the larger trunk horizontally toward the right. Okay, so if you want a system diagram, let's do it like that. And so the person is pushing this way to the right. This is a level surface, I'm assuming. The coefficient of static friction between the trunks and the floor is 0.35. So mu S is static friction, right? Yep. Equals 0.35. Right. Now it says determine the magnitude of the maximum force the person can exert without moving either trunk. So we're looking for Fs max here. So mu S equals Fs max. That says Fs max clearly over Fn. So we're going to solve for this. So this is 0.35 equals, I'm just going to say F for now. These are going to be combined. So that's 86. 86 times 9.8, because that's normal force, mass times gravity. So this Fs max is 0.35 times 86 times 9.8. Fs max is 0.35 times 86, not minus, 0.35 times 86 times 9.8 is 294.98. 294.98. Sig figs is 2, so that's going to be 290 newtons. That's the question. This is 1A. It said determine the magnitude, so you don't need a direction. That's 1A. Let's do 1B. 1B says calculate the force the larger trunk exerts on the smaller trunk. All right. So this is the applied force here. Maximum applied force was 294.98, and it didn't move. So think of this: mu s equals Fs over Fn. Now that we know this, we can figure out because it's the maximum amount of force, right? So we figure out the maximum force based on just the smaller one. Before we had combined weights here, now it's going to be just the smaller one. This is question B, by the way. So mu s is 0.35, so we have 0.35 equals Fs over the smaller weight, smaller mass, weight, look at me, smaller mass, 34 times 9.8. So 0.35 times 34 times 9.8, 0.35 times 34 times 9.8 is 116.62. 116.62. Sig figs, 120 newtons. That's the amount of force that the bigger box is applying to the smaller one. So basically what's going on, to kind of understand this, we have the two boxes here. Force is being pushed. Part of the friction from this box, so what's kind of going on right here, this is slowing things down before the force gets to this one. There's only 120 newtons left for this one with sig figs, 116, blah, blah, blah. But that's what's left for this one. Hopefully that makes sense. You can kind of rationalize what's going on. Because if you're just looking at the numbers, you might be just kind of figuring out how to get the right answer. But this is why. It was, what was the total? 290 newtons was being pushed. This is stopping 170. Okay, the friction is stopping 170. So there's 120 left for that bad boy. Part C, would either answer change if the person pushed in the opposite direction on the smaller trunk? Our part A, like the total amount, no. The total amount's not going to change. So let's say we're pushing this way. The total amount of force would not change. But the amount of force being applied to the bigger one, yes. Because this smaller box, so for part B, the answer would change because this smaller box would only kind of provide this much resistance with sig figs. This is really what it is. But would only provide this much resistance, so the bigger box would stop the rest of it. Hopefully that makes sense. This is going to be long. I hope I don't make any mistakes because of the one-shot recording. All right, question number 2, page 174. It says a 4-kilogram block of wood, there's a diagram for you. The 4-kilogram block of wood sits on a table. A string is tied to the wood, running over a pulley and down to a hanging object. The greatest mass that can be hung from the string without moving the block of wood is 1.8 kilograms. So it's talking about greatest mass without moving it. So we're talking about static friction here. Calculate the coefficient of static friction between the block of wood and the table. Okay, so the amount of force, the amount of applied force here, which FA is going to be kind of, it's like FG, for that hanging piece, which is 1.8. So this is mass times acceleration. So the mass of that hanging weight, that's what's providing the kind of applied force here. This is what's pulling, 1.8 times 9.8. 1.8 times 9.8 is 17.64. So that's the applied force by that little weight. And what's the question again? Calculate the coefficient of static friction between the block of wood and the table. Okay, so mu s equals Fs over Fn. 17.64. What are we doing? Coefficient here? Yeah. 17.64 is going to be, this is the maximum amount of force, so that's going to be our Fs. We can figure out Fn based on the bigger block and gravity, and then we're going to have this. So 17.64, not worried about sig figs yet. Fn, so the bigger block is 4.0, 2 sig figs, 4 times 9.8. This will give us our coefficient of static friction. 17.64 divided by 4 equals that, divided by 9.8, 0.45. No units. That is the coefficient of static friction on the big box. Cool. All right, next practice. So this is now page 175. Page 175. Number 1. Two people start running from rest. The first person has a mass of 59. First person, M1 equals 59. And is wearing dress shoes with a coefficient of static friction of 0.52. Mu s equals 0.52. A mu s for that first person. I should write a bit bigger so these things will be clear. Mass of the second person, where I lost my spot. Mass of the second person is, nobody cares apparently. The other person's wearing running shoes with a coefficient of static friction 0.66. Okay, I don't know why that one's not there yet. Let's see. Nope, this is 2 equals 0.66. All right, number 8, it says calculate the maximum possible initial acceleration of the person wearing dress shoes. All right, so we have, so we're talking about the first person here. So mu s equals Fs over Fn. Let's plug in what we know here. Mu s is 0.52, which equals Fn is going to be 59 times 9.8. So we are figuring out the maximum force of static friction. So what this is going to tell us, this is one of those cases where friction helps us. This maximum static friction stops him from slipping in his dress shoes, or her dress shoes, whoever this is. I don't know the gender. So we're going to figure out the Fs max here, which is 0.52 times 59 times 9.8 is 300.664. 300.664. And you're thinking, yeah, but this is asking about acceleration. We need this first because F equals ma. Force of 300.664 equals the mass of this bad boy is 59 times acceleration. So 300.664 divided by 59 divided by 59 equals 5.096. Acceleration equals 5.1 meters per second squared. Is it asking magnitude? No. So you've got to give a direction. If you're not sure, say forward. Because I'm assuming he's not going to be running backwards. Maximum possible acceleration. Okay, so part B says explain why we do not really need the mass of either person when finding the initial maximum possible acceleration. Good question. Because the reason we don't need that, oh, this is for B. The reason we don't need that is because if you look back up to here, This became the 300. 300 is mass times acceleration. So really, this is mass times acceleration over mass times gravity. The masses would cancel. F equals ma. This is from this. The force that we got from that equals mass times acceleration. We would have 59 on the top and the bottom solving for A. That's essentially what we're doing. Hopefully that makes sense. Part C says determine the ratio of the two accelerations and compare it to the ratio of the two coefficients of friction. This is one of those questions where it's not a question you need to solve as much as it's trying to teach you with this. So I'm not going to do it because you were just doing the exact same thing and then you're just comparing ratios. I'm not going to ask you any ratio questions. But it's just trying to show you that basically your situation mu equals acceleration over gravity in cases like this. This is what it wants you to see. So it's showing that the ratio of acceleration, the ratio of the coefficients of static friction are directly related to the accelerations. Okay, cool in the gang, cool. Let's move along. We're not even done the second practice out of 3 practices. So this is number 2 on page 175. What time is it? I'm going to get to SLG soon, if anybody's there. A skater with mass 58 kilograms. 58 kilograms is holding one end of a rope and standing at rest on ice. Of course they are. Assume no friction. All right. Another person with mass 78, so that's M1, M2 equals 78, is standing just off the ice on level ground and is holding the other end of the rope. The person standing on the ground pulls on the rope to accelerate the skater. Well, it's a skater. Oh yeah, it says a skater. Forward with no friction. So maybe it's super dull skates. The coefficient of static friction between the ground and the off-ice person is 0.65. So this dude, mu s equals 0.65. Calculate the maximum possible acceleration of the skater. All right, so we're figuring out the maximum force that this dude can pull without himself slipping, and then apply that force to this person with no friction slowing them down. So we're looking at person number 2 first. So mu equals Fs over Fn. Mu s is 0.65. Solving for that force, and they are 78 kilos multiplied by 9.8. So Fs is going to equal 0.65 times 78 times 9.8, 496.86. 496.86. So this is the maximum amount of force that the 78 kilo person can pull without themselves slipping. So now we're applying this amount of force to this mass. F equals ma. 496.86 equals, in the mass of person number 1, it's 58 times acceleration. Divide both sides by 58. 8.56, blah, 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 so it's going to be 8.6. Acceleration equals 8.6 meters per second squared, and probably going to be forward. Burp. Hopefully that makes sense. Sorry, I maybe skipped a step. Am I already breaking rules? This was the answer, but 2 sig figs. 2 sig figs. Some of you guys, goodness gracious, you need to start learning to love your sig figs. Okay, that's practice dose. Now, woof, this next practice looks massive. Good times. All right. So this now is page 177. Practice 1. A 0.170, 3 sig figs, hockey puck So M of the P equals 0.17 kilograms. Watch, when it's talking about a hockey puck, it very easily could have said 170 grams. We need things to be in kilograms. So watch for that. Every once in a while it'll say it's, or it's 1.8 grams or something. Change it to kilograms. This one, it's in kilograms, so we're good. So it's initially moving, oh, here we go. It's initially moving at 21.2 VI. See where this is going? 21.2 meters per second, 21.2 meters per second, blah, blah, blah. I don't need to write that down. Along the ice, the coefficient of kinetic friction for the puck and the ice, mu K equals 0.005. What are they going to want? What is the speed of the puck after traveling 58.5? Okay, so maybe one of the little steps I'm going to skip is I'm not going to do the kind of the 5 equation type of questions because that's not new, but I'll do the new part of it. So then what we need to figure out here is what is the deceleration, the negative acceleration of this puck. Because once we have that, then we'll have acceleration. What else is it giving us? So the displacement is 58.5. D equals 58.5. So we're going to have initial velocity. We're going to have displacement. We're going to solve for acceleration. And then we're going to need to, what is the speed? Then we're going to find VF. And by we, I mean you, if you want to. The important part of this unit, the new part, is finding that acceleration. So mu K equals Fk, force of friction, over normal force. Mu K, 0.005. Fk, yeah, we don't know that, so we're solving for. Silly. Fn is the mass of the puck, which is 0.17, times 9.8. So 0.005 times 0.17 times 9.8, 0.00833. This is the force of friction. Now we need to find the acceleration. This is one of those cases where it's like it's ma over mg. We could have canceled the m's there. Because this equals mass times acceleration, and the mass is 0.17 times acceleration, 0.00833. I'm going to have to get a new marker. Divide both sides by 0.17. 0.049. 0.049 equals A, which is negative. When we put it over here, when we put it into our questions, it's negative because it's opposing motion. We're moving in one direction. The acceleration is going against that. All right. Now that you have this negative acceleration, you've got initial velocity, displacement, negative acceleration. Just plug it into the formulas to get final velocity. I'm going to throw this marker along with this paper. And go to number 2. Am I going to finish before... What? Don't have any more markers? Yeah, I do. Before SLJ. Okay, number 2. Maybe I can pause this. I'm not sure if I know how. 2. Oh, pretty new marker. A snowmobile used to pull 2 sleds across the ice. There's no way I'm finishing this in 10 minutes. A snowmobile is used to pull 2 sleds across the ice. The mass of the snowmobile and the rider is 320 kilograms. Mass of the snowmobile is 320. Oh, that's a nice marker. It feels really good. Lost my spot. The mass of the first sled, M1, equals 120. Look how clean this is. Mass of the second sled is 140. I have a feeling our total mass is going to be needed at some point, so I'm just going to figure that out right now. Total mass is 580. Is that right? 3, 4, 5, 2, yeah, 580. Okay. The ground exerts a force of 1,500 newtons forward on the snowmobile. that's it. What that's saying is, it says the ground is exerting this force forward. That's because the snowmobile is exerting 1,500 newtons of force backwards. It's kind of like if you're walking. When you are, can you see this? When you're walking, you are pushing on the ground. If it's slippery, you slip like this. If it's not slippery, you walk because you're pushing backwards. What a weird video is this? You're pushing backwards on the ground, and that means the ground is pushing you forward as well. I'm explaining this because of the way that question was worded. So basically, it's 1,500 newtons of force really is what the snowmobile is applying to the ground. The coefficient of kinetic friction for the sleds on the ice, so for these two bad boys, mu k equals 0.15. Assume that no other frictional forces act on the snowmobile, so this guy is free and clear for whatever reason. Calculate the acceleration of the snowmobile and the sleds. All right, so what my spidey senses are telling me is this is the applied force, but we need to figure out the frictional force, subtract it from this, and then we'll figure out our acceleration. So let's figure out frictional force. Mu k equals Fk over Fn, which is ma over mg. Paching, we can cancel those masses. Mu k is 0.15 equals acceleration of the force friction. Oh, you know what? We're going to want the force. We're going to want the force because we have to subtract it from here. It's not just the acceleration of these bad boys that we want to figure out. So their masses together are 260 times 9.8. All right, so 0.15 times 260 times 9.8. So Fk equals 382.2. So we're going to subtract 382.2 from 1,500. Now, if I would have did this acceleration thing, I could have figured out what the acceleration of this would be with no friction. So if I figure that out, so just this divided by the whole shooting match, everything, of what the acceleration should be without friction, then I could just find the difference if I figured the acceleration out here. Make sense? Regardless, I'm gonna figure out the net force. So F net is 1,500 minus 382.2. A lot of noise in the hall. How many people are here? 1117.8. 1117.8. This is the net force. F equals MA. 1117.8 equals, so now it's the total mass of everything. That's 580. Remember we figured that out earlier because we was smart. 580 times A. Divide both sides by 580. 1.9. The sig figs? Is that sig figs? 2 decimal places? Yeah. The acceleration is 1.9 meters per second squared. Did they give us a direction? Forward. Surprise, surprise. That is practice number 2. I have 2 more questions to go, but I got to get to SLG. So I'm going to pause this. Wow, half an hour in. I'm going to pause this and hope I can unpause it. I don't know what I'm doing. Oh, look, I unpaused it. You guys don't even know how long I was away for. Should I even tell you? Maybe it's none of your business. I had 1 person in my SLG. That's good. And then 1 person came late, but I had already dismissed. All right. Number 3. Page 177. A string is tied to a 3.2 kilogram object on a table and a 1.5 kilogram object hanging over a pulley. The coefficient of kinetic friction between the 3.2 kilogram object and the table is 0.3. 3. All right, so M1 equals 3.2. Oh yeah, I got a nice marker. M2 equals 1.5. Mu S, which is related to the first mass, equals 0.330. Well, Karina Reimer's messaging. Wait till I'm done the lesson. I don't know if you guys can hear that ding. Anyways. US equals 0.3. Now I'm all distracted. Calculate the acceleration of each object. Okay, so you've got this situation. Hey, that's not bad. This is like the best thing I've ever drawn. So you've got the situation. This is the applied force. We're going to have applied force based on gravity and the mass of this bad boy. And then you've got friction, which is going to be an opposing force. So we're going to have to figure out the net force before we can figure out the acceleration. So we'll say the applied force, Fa, is going to be 1.5 mass times acceleration, 1.5 times 9.8. 1.5 times 9.8, 14.7. So that's the force going down. Now the kinetic friction force, so Fk, well, I could set it up that way, but I'm going to do it this way. Mu k equals Fk over Fn. If you wanted, you could say Fk equals mu k times Fn. The textbook probably shows it in this orientation sometimes too. So mu k is 0.3. Normal force for the big box is 3.2 times 9.8. So the force of friction, which will be negative compared to this, 0.3 times 3.2 times 9.8 equals 9.408. So our net force is this, our net force kind of as far as the motion in this. F net equals 14.7 minus 9.408. 14.7 minus 9.408 equals 5.292. Now this will equal mass times acceleration, so we can solve for our acceleration, which is the mass of both of these bad boys. So that's 4.7. Just did that in my head quickly. 3.2 plus 1.5, 4.7 times acceleration. This is 5.292, so divide both sides by 4.7. The acceleration is 1.1, okay, with sig figs. 1.1 meters per second squared, so it's to the right or down, depending on which object you were talking about. Okay? That's 3A. That's just A, brothers and sisters. 3B says determine the magnitude of the tension in the string. I don't need much space for this, I don't think, but whatever. So 3B. Determine the magnitude of the tension in the string. Oh, I need that other paper, actually. I don't know where to put it. So the force of that of the mass just going down. Let me get a different color. Do I have a different color mark? Oh, I got a red one. So the force of that. Where are we? Oh, so here, here's our. No, that's wrong. Maybe I'll just I'll just kind of start over. So the force in that string pulling down, so F equals MA. The force is 1.5, because that's the mass of the little guy, times 9.8. 1.5 times 9.8 is 14.7. That's the mass of it going down. It's 14.7. But friction is kind of coming along. Sorry, not friction. How do I explain this? Okay, so what's going on is it's 14.7 newtons that's pulling down on this. That's if it's just hanging, right? So if this was just moving, like there was no kind of resistance, then it would keep going. If this thing wasn't moving at all, then it would be 14.7, but it's moving. Is I guess what I'm trying to say here. This thing is moving, just not super fast. Friction, force of friction, I'm getting this other paper again, is 9.408. So this is, I'll say, the force due to gravity. Force of friction is 9.408. 14.7 minus 9.408. Something feels wrong about this. 5.92 tension in the string. Yeah, no, it's got it as 13. Give me a second here. I'm going to pause it because I'm confusing myself. Realized what I did wrong. Silly, silly, silly. The acceleration, it's not doing 9.8. It's doing 1.1. Remember that? Remember that part? So it's 1.5 times 1.1, because that's its acceleration. 1.5 times 1.1, so that's 1.65. That's the force in it, but the friction is slowing it down. Okay, friction is pulling back. The force of friction was the, where was it? Hang on. I think I got it now. I think I got my brain screwed on right. This is the little one pulling. We also have to consider that big one. So this little one is 1.5. The big one is 3.2. Now my reason for this, well here, I'll just write it out first. 3.2 times 1.1. It's 3.5. Now, what's going on is you have to consider this is the lighter one. It's pulling on both ends. So it's going to be the greater of the two that's pulling on both ends. Now we add this, because this is from the bigger block, we add this to what I blocked out before, the force of friction. 3.52 plus 9.408. 12.928. Sig fig's 13. I think that should be right. What's the answer say? Yeah, there you go. So it's 13 newtons. So after all that confusingness, sure glad I recorded it all. What I want you to take from it is, imagine you had like a pocket watch, on a string, or just something on a string. I don't care, and it's really light, and you're spinning it around in circles. Okay, so you're holding something, and then you're this thing is spinning around in a circle. Now, if it doesn't weigh very much, there's not going to be a whole lot of tension in this string. But if you swing it super hard, you really, really crank it, you're adding tension to that string. Try and think of it that way with this pulley. This bad boy isn't pulling that much on it, but this one is. That the force of friction is also pulling on it, is increasing it. If there's no friction here, there'd be like no tension. It would just go. But the friction is adding to that tension. That's a tricky one. Man, I hope that makes sense. Should we do one more? Might as well. Goodness, this is ever. Last one. Last one. Number 4. An electric motor is used to pull a 125 kilogram box. M1 equals 125. Across the floor using a long cable. The tension in the cable is 350 newtons. So F T equals 350. And the box accelerates at 1.2 meters per second acceleration. So that's going to be the net acceleration. I'll tell you why I'm saying that right away. 1.2. This happens for 5 seconds. The cable breaks and the box slows down and stops. The cable breaks. Why is the cable breaking? Because of friction. If there's no friction, it's going to be easy or easier, but friction is what's slowing it down. And the reason, well, the question's asking, calculate the coefficient of kinetic friction. So here's the thing. With a force of 350, I said the net acceleration is 1.2. We can figure out what the acceleration would be if it was frictionless. Okay, F equals ma, force of 350, mass is 125, a, divide both sides by 125, 2.8. So acceleration without friction would be 2.8. That's why I said this is the net acceleration. It's only going 1.2. So that means there is a 2.8 minus 1.2. There is a kind of a 1.6 meter per second squared deficit. Why? Where did this go? This is due to friction. So there is a negative 1.6 that's added to the 2.8 to give us 1.2. It's negative because it's opposing motion. If we want to figure out now the coefficient of kinetic friction, that's what the question's asking? Yeah. So mu k equals Fk over Fn. Mu k, we don't know. So, but Fk is the mass, 125, times 1.6. This is the force of friction, mass times acceleration. This is the acceleration of the friction, divided by normal force, which is 125 times 9.8. We can cancel these bad boys. 1.6 over 9.8. 0.16. So the coefficient of kinetic friction is 0.16. This is getting trickier. I can feel it. That's why you can ask questions like crazy. B. How far does the box travel up to the moment the cable breaks? How far does the box travel the moment the cable breaks till it stops? Okay, I'm not going to do those. Those are just punching into the 5 equations. If you're not comfortable with the 5 equations, do this. Do this because that means you need the practice. You just punch in the numbers in. For those of you who are super comfortable with that, you can skip it. Now here's the thing. I'm looking at the clock and it says this video is 43 minutes and 30 seconds. If I were in class right now with you, I would have been going slower because people would have been asking questions for clarification and things like that, and would have been pausing to write things down. This would have taken probably the whole class. So if we were in class together, what I would do is say, you can start this assignment, but I'll give you class time on Monday. So that's what I'm going to do. There will be no new assignment on Monday. Don't procrastinate. Do the work. But we're not doing anything new until Tuesday. Hopefully that makes sense. Sorry about the gong show with the other question. Yeah, be well. Take care. Peace.